I said there'd be 2 problems on it, and there still are, but now there's another problem, which is just for extra credit from chapter 9. I mean, I had to rope chapter 9 in somewhere, since we apparently are going to be finishing chapter 9 before you even take the midterm. So, whatever. Anyway, so that's the plan. Before we begin, are there any questions? Obviously, Octavio can't answer since he's only going to see the recording, but is the other guy on, is anybody on? No, okay. Well, they can all see the recording, whatever.
Yeah.
Okay, so last time we sort of left off in the middle of section 9.6, and when I took time out to do problem 14 for weirdo reasons, which I sort of explained at the time. By this time, I'm sure you've all gone through section 9.6. The major thing about the chapter is actually, in addition to just sort of setting the stage with what we want is a complete set of commuting observables, which is what they say the title of this is. What they want is to construct eigenstates which are simultaneous eigenstates of h, L squared, and Lz. And as you remember, as long as all of the operators in a particular set mutually commute, there are eigenfunctions which are eigenfunctions, simultaneous eigenfunctions of all of them. So we're going to label the eigenfunctions that are such eigenfunctions with the eigenvalues of each of the operators. So E and I think he uses little l. Yes, he does. And little m. And these are such that if you operate with h on this, you get E, L, m. If you operate with L squared on this, you get h bar squared L times L plus 1 times E, L, m. And if you operate with Lz, you get h bar m. And you may remember these guys from, they have almost exactly the same structure as what we learned in chapter 3 for states that were eigenfunctions of the J squared and JZ operators. I said almost the same because depending on what kind of J it was, little l, which was little j, could be also half integer. And here we're going to find L can only be integer. So no half integers for the orbital angular momentum. So it's not exactly the same as J. And the other thing that we didn't do in chapter 3 was actually construct what the position space, what these eigenfunctions look like in position space. So we're going to do that. In this particular section, what he does is he reworks the Hamiltonian. Remember, the original Hamiltonian that we had was p squared over 2 mu plus v of r, where here this represented the relative coordinate and this the momentum. So we've taken out the momentum of the center of mass, and we've taken out the we've transformed the variables from the, right, okay. So we did that all in section, whatever the heck it was. I don't remember what it was, but that's right, we did that. Yeah, in relative and center of mass coordinates. So this was section 3. So if you need to go back to that, you can. This is the relative momentum operator, little p, defined on page 311. And this is the relative coordinate r, defined on that same page. So we're imagining that we have a Hamiltonian which is a function of, which has the kinetic energy in it, but whose potential energy is, and I did not put a hat on this because what he's thinking of here is that v is only a function of the magnitude of r, the distance between the two particles, not a function of the vector r. So if that is the case, then what we can do is we can take the Hamiltonian in spherical coordinates. So we're now transforming from, instead of thinking of p squared as px squared plus by squared plus pz squared, instead as the p operator, which we're going to only look at as a in spherical coordinates. And in that case, we can transform the kinetic energy term, as it says in equation 911, to, so this is the what things look like in coordinate space. So this has two pieces, d squared dr squared plus 2 over r d by dr of r psi plus r L squared psi over 2u r squared. Now, we can make this look a little bit better by transforming the this part of the kinetic energy. So, and he promises that this is what a lot of people call a forward reference, which is a little annoying. He's referencing something that he's not going to do until chapter 10. So as I say, it's a little annoying, but if you can just accept it for the nonce, then we don't have to go to chapter 10 and actually go through that. We promise that we are going to do that in the very next chapter. So this is what p sub r, that is not the full p squared, but just the part in spherical coordinates that's dependent only on the momentum in the radial direction. So this would be just the PR component. So we're thinking in spherical coordinates now. This is, as he says, he derives this in chapter 10, and this is h bar over I d by dr plus 1 over r psi, which means that this is what the PR operator goes to in spherical coordinates in coordinate space, in real space. Okay, and then in terms of that operator, then we can just write this part. Oh, I guess I should have put this in parentheses anyway. This part just as r PR squared psi over 2u. So it has exactly the form that we would want for the kinetic energy in spherical coordinates, p squared over 2m essentially. And then, of course, if we're thinking of a set of states which are simultaneous eigenstates of all three of these operators, then this guy becomes very easy to, the final term becomes very easy to evaluate also, and that's on the following page, 320, where he says, okay, the whole equation is now just a function of r, and we can just divide out the angular sort of bit to it. So we end up with a radial differential equation only in r. That's a one-dimensional Schrödinger equation, which is really cool, because we already know how to deal with one-dimensional Schrödinger equations. We spent a whole chapter on it in chapter, 6, I think it was. So, I mean, it's got a little bit of weirdness to it in the fact that it doesn't look exactly the same as what we had in chapter 6. But it's in spite of that, it looks very nice in the sense that it is a one-dimensional Schrödinger equation. So we're making a further simplification by making the radial part of the wave function defining u as just the radial part of the wave function times little r, where little r again is just the distance between the two particles. And then we get the very simple thing, minus h bar squared over 2 mu d squared dr squared plus L times L plus 1 times h bar squared over 2 mu, right? Oh, 2 mu r squared plus v of r. This whole thing operates on u of r, and you get finally the energy. Okay. So this is a one-dimensional Schrödinger equation. It looks exactly like what we had earlier, which was minus h bar squared over 2m d squared dx squared plus v of x, all operating on psi of r to give e of r. Excuse me, e times psi of r, sorry. I don't know where my brain is today. In other words, this guy here fills the role of v of x. This guy here, I mean, it's got a mu instead of an m, and it's got an r instead of an x, but you know, that's just a name. We're not worried about names, right? So he points this out at the bottom of page 320 as to how much we've managed to simplify the three-dimensional Schrödinger equation all the way down to a one-dimensional Schrödinger equation, although we still have to solve the angular problem. And that's what we're going to do in the very next section. Right. So that was essentially what there is in section 6. Of course, please read it for yourself. And there's one problem on section 6 that I did not assign to you, and that's number 12. Oh no, that's really on section 7. All right, let's go on and talk about section 7 then first. All right, so, any questions about this stuff? Pretty simple, straightforward stuff. Most introductory courses on quantum mechanics split out the radial and angular parts using separation variables, which was the same technique that they use for separating out time and spatial variables in the time-dependent Schrödinger equation. He doesn't do it that way, and I actually appreciate the difference in the ways, but if you want to see it done the quote-unquote normal way, any of a number of books do it, like my favorite is Griffiths, but please yourself. All right, so let's talk a little bit about section 7. Section 7 talks about, it sort of creeps up on the spherical harmonics, talking about vibrations and rotations in a diatomic molecule. Now, what is a diatomic molecule? Well, here it is right here. The ball and stick model, all right? Molecule. There we are. All right, so here we have a diatomic molecule. I think his example is HCl. Yeah, HCl. So here's the hydrogen, here's the chlorine. It doesn't actually look like that, actually, of course. If you actually look at these things, it actually more looks like this. But, ball and stick model, ball and stick model. Hydrogen's little and chlorine is big and fat. Anyway, why are we looking at diatomic molecules? Because we want to solve that, eventually we want to solve for the hydrogen atom. And what we want to do is sort of, wet our feet just easily by looking at a very simple model for which we want to use the harmonic oscillator and rotations which are going to be eigenfunctions of L squared. What am I talking about? Well, if you have a molecule, in general, this is what the bonding Born-Oppenheimer surface looks like. So this is the energy on this axis, and this is the distance between the two atoms on that axis. This is my very bad representation of figure 9.4. So this is the potential energy as a function of distance between the two molecules. In other words, there is a bonding, there's a minimum to this energy. Okay, a place where dV/dr is 0, right? This is V, right? Everybody okay? And that's called the equilibrium bond length. Dot, 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 dot. Usually called R naught. Right, it just is. Right? But if you look at the bottom of this potential well, it's, harmonic, more or less. Okay, that is, here I am waving this thing around again. I'm a terrible person. I'm going to use red. Okay, that is, it's harmonic in the sense that we can sort of fit a harmonic oscillator to the bottom of it. Why can we fit a harmonic oscillator to the bottom of it? Taylor's theorem. That is, if you are near enough to a minimum, the restoring force is near enough to linear. And that's Taylor's theorem, right? And if the restoring force is linear, then the potential energy is quadratic. So that just means if you are at a minimum in energy, and if you're close enough to the minimum in energy, you can model it as harmonic. And it's just from Taylor's theorem, that's all it is. But the nice thing about that is, that gives us a really simple, easy model for molecular vibrations. We just use harmonic oscillator. And so we could say that the vibrations of a diatomic molecule are well described by, let's call it H vibe. 1/2 m omega squared x squared, where x here is the deviation from the R naught. Okay, piece of cake. And we know exactly what the eigenvalues are. These are, I think he calls them E sub nu, or N sub nu, sorry, En sub nu. A lot of subscripts there, which is H bar omega N sub nu plus 1/2. Right? So this is just harmonic oscillator energies. And that's all we're going to do for the vibrations. What about the rotations? Okay, well, the rotations in general are energy levels within the vibrational levels. That is, vibrations are in the energy scale in the IR. Okay? Rotations are in the energy scale in the microwave. And in fact, that's how a microwave oven works. It's tuned to part of the band of the rotational absorption of water molecules. So what a microwave oven does is rotate the water molecules in your food. And since most food is mostly water, it'll heat up food. Right? Why don't you want to put metal in a microwave oven? Because arcing. Metals conduct at those frequencies. And so if you put metal in there, you'll get, and it'll burn out your cholesterol, so don't do that. Everybody okay? Great. All right, so we're going to do the rot-vibe spectrum here. All right. So what we would think about this is, here's the thing that we're modeling our V of R as, and then inside V of R we can write down or we can draw in what the vibrational levels are. This would be n equals 0, n equals 1, n equals 2, and so on. And these are equally spaced according to this formula. But then within the vibrational levels, there are rotational levels. And remember, those are much smaller in energy. Okay, so they're on top of the vibrational levels. So we can imagine them as being, and then we've got, so I can't draw. But these are much more closely spaced on this energy diagram. As you can imagine, because the difference between those is in the microwave part of the spectrum, whereas the difference here is in the IR part of the spectrum, much higher energy. Everybody sort of okay? All right, great. So how are we going to model that? Okay, this was H vibe. What will H rot look like? Well, we're separating the vibration part from the rotation part. Now, this is not exactly correct, but then this wasn't exactly correct either. I mean, this is the correct V of R, and we're modeling it as this. Right? So, you know, it's a model, all right? So be patient. So what we're going to do is we're going to separate out the vibrations from the rotations on the basis that they're very separated in energy. So that means that if we excite a vibrational level, it's not going to do anything to the rotational level to 0th order. Right? So what would the rot part look like? Well, the rot part, H rot, would look like L squared over 2I. Where L is the angular momentum operator, L squared being the the square of the angular momentum operator, and I is the rotational inertia. And this is just like what we learned in freshman physics, except of course here L is the operator. I is still I, but L is the operator. Okay, that's equation 9106 right there. And remember from the previous section, we're thinking about states which are simultaneous states of energy L squared and LZ, right? And that means that if we're in an eigenstate of H rot, let's just call it L, H rot on L and M, well, that just gives me H bar squared L plus 1 over 2I. And H bar squared and 2I are all constants, just numbers. Oh, sorry, times the same state back again. Sorry. State by Mitnick. All right, so that's at the bottom of page 323. Everybody okay? Also okay? Great. All right. Excellent. So if we put these two things together and say that the total Hamiltonian is H vibe plus H rot, then if H operates on E, L, M, we get H bar omega n plus a half plus H bar squared L plus 1 over 2 mu, all operating on E, L, M. And that's equation 9111 at the bottom of page 325. So far, so good. Might be worthwhile reading through this section and looking at the graphs. And finally, we get to 9.8. Everybody okay with this, though? It's pretty simple and straightforward, I think. All right, finally in 9.8, we're going to get to this position space representations of L in spherical coordinates. As I said at the beginning of the lecture, in chapter 3, we didn't do position space representations of the J operator. Because why? Because we hadn't done position space representations of anything yet. That had to wait until chapter 6, I think. Right? But the same kinds of things apply to any kind of thing that has a spatial rotation. Okay? So here we're going to find in this section what the eigenfunctions of capital L squared and capital LZ look like in spherical coordinates. Oh, stop that.
You can use the other side of the board too if you want.
My goodness, I can. I've just been neglecting it, haven't I? Ah! Woot, woot. All right, so section 8. L, M, in sph chord. So how do we do this? Well, we do it with the same approach that we had in chapter 3 and that we had at the beginning of chapter 9. That is, we consider an infinitesimal rotation around the z-axis. Okay? So if we do that, then if we have R dagger d phi comma k. So this is a rotation, all right, so r, regular r, d phi k. This was a infinitesimal rotation around the z-axis, and we know what that does. This transforms us into, oh dear, 975. All right, I'll have to look at 975 because I don't want to mess up my sign here. Ah, here it is. This is on page 316. This guy operating on r theta phi gives us r theta phi plus phi. Sorry. Okay. So what he's doing here is he's saying, okay, let's daggerize this entire equation. So that whoops it around, and then we can think of this as r theta phi. That's the dagger of this, gives me this, and this is r theta phi plus d phi, which means that, r of d phi k hat operating on r theta phi backwards gives me r theta phi minus d phi. Because remember, r dagger r gives me the identity. In other words, if I rotate a little bit around the z-axis in one direction, and I rotate a little bit around the z-axis in the other direction, I get one. Okay, so that gives us a differential equation for r. Right? So now let's take this entire equation and multiply it on the right with psi. Right? That gives me, on this side, it gives me r theta phi psi minus d phi d r theta phi psi. And that gives me a differential equation, so we can now say that this guy here is 1 minus I over h bar Lz d phi. So this is all on page 328. So this is how we get a differential equation for the Lz operator. In other words, Lz in spherical space just becomes, is h bar over I? Yes! h bar over I d by d phi. Okay, so that's the z component of the orbital angular momentum. And this shouldn't surprise us, because we remember that a linear momentum is also represented in position space, this time in Cartesian position space, by a differential operator. So in other words, and he points this out too, if you have px, what does that look like in position space? Well, that looks like h bar over I d by dx. I guess I should have put partial derivative here. So this is something that doesn't surprise us just because we're doing an angular momentum instead of a linear momentum. But it does give us a differential equation that we can use to determine what the eigenfunctions of Lz look like. We already know that if Lz operates on L comma m, we get h bar m times Lm back again. But now we know what Lz is in spherical coordinates. So we can just plunkle that in and take this whole equation and multiply on the left by r theta phi. and imagining this operating backwards. And that gives us the differential equation for the LZ operator, which is just that the LZ operators, differential equation for the eigenfunctions here, which just gives us H bar over I, d, I guess I should, d by d phi of r theta phi L m equals H bar m r theta phi L m. And we can solve this differential equation instantly. If you take a derivative of this function, which is a wave function in spherical coordinate space, then if I take the derivative with respect to phi, I get back a number times the same function back again. That sounds like an exponential to me, right? And in fact, it is. Okay, the h bars go away, and I can take the I over to the other side, and I just get that this function here, at least the part of it that depends on phi, is just e to the I m phi. Where, as we're going to find out, m is an integer. How do we know that m has to be an integer? Well, remember that m had to go from minus L to plus L when we did components of the angular momentum in the z direction. Okay, and L is going to turn out, as I say, we haven't shown that yet, only to be an integer. So m can only be an integer as well. There's one more thing that we should say about the eigenfunctions, the piece of the eigenfunctions that we're looking for. That's the function of phi, and that is that we want it to be single valued. So all that means is that if we add 2 pi to phi, we want to get the same number back again. We want to get the same function back again. We want it to wrap around and come back on itself. Okay. So that means that, again, m has to be an integer. So this, if that is going to be true, then m has to be an integer. 0 plus minus 1 plus minus 2 and so on. So that's also important. Oh. Okay, going over to 330 now. What we're going to do is we're going to transform the rest of L. Okay, this is LZ. Okay, we also want LX and LY. So how do we get LX and LY? Well, we remember that L has to be, that the full L has to be R cross P. I guess I'll put a hat on that also. And R cross P in coordinate space looks like R cross H bar over I P in coordinate space, right? Or excuse me, H bar over I del. Sorry. Where's my brain? I don't know. Okay. So we're going to transform that gradient, that del operator, into spherical coordinates. And I can never remember how to do that, so I always look it up. Fortunately, there are books where you can look it up. I have a CRC math tables, and maybe you do too, or you can look online, I suppose. And so you get, if you do that, that L goes to, this in spherical coordinates is H bar over I, unit vector in the phi direction, d by d theta, minus unit vector in the theta direction, 1 over sine theta d by d phi. Okay, and if we take the x and y components of that, we get Lx and Ly. So those are equations 9, 127 and 9, 128. The final sort of conclusion for this for L squared, equation 9, 129, is problem 14, which I did for you at length on Monday. So I hope or Wednesday, I guess, of last week, so I hope you remember it. But the very, very nice thing about that is that we can express the whole Hamiltonian for that we wanted to get earlier in terms of spherical coordinates, and that's 9, 131 at the bottom of the page, and that's the end of section 8. Everybody sort of okay? Maybe. Section 9, which is the last section in the chapter besides the summary chapter, shows how you get the spherical the spherical harmonics y. All right. In other words, the spherical harmonics y, which are always written as y Lm of theta and phi, are the product of the functions we already derived in the phi direction and the where are we? The guys in the theta direction. So this is capital theta of theta times capital phi of phi. Okay, and that's the equation at the very top of the page 332. He then says, okay, we've already derived what Lx and Ly are. Let's write the addition and subtraction of those two as L plus and L minus. So in other words, we're defining from these guys that we already found out, L plus and minus as Lx plus or minus I Ly. And it will turn out that these guys actually make us go up or down in Lz, or in other words, in M. The spherical harmonics are a complete set, and the first few are listed on page 334, and they're pictured on page 335. It's always nice to have a sort of picture in your head. Now I'm going to do one of the earlier problems on this so you can see how we can just manipulate them. Oh, I forgot to do number 10. Okay, can we go back to number 10 because it's about the, I cleverly just erased that. But then I'll come and do the thing on the spherical harmonic. I have it in my notes, but I'm sorry it's out of order here. All right, so before we do number 12, let's do number 10, which is about the energy spacing between the vibrational energy levels of HCl is 0.37 EVs. Okay. So this is supposed to be a fairly simple prob on that rotations and vibrations of a diatomic molecule section. So this is number 10. And we're given that delta E vibe is 0.37 EVs. And we remember that the energies, the vibrational energies, are n plus a half times h bar omega. So the difference between energy levels is h bar omega. Is that sort of clear? Yeah, pretty obvious, okay. Okay, so, all right. In part A, we're asked what is the wavelength of a photon emitted in a vibrational transition? Well, we know that the wavelength of a photon emitted is going to have an energy equal h bar omega, right? And we know that the, or HF if you prefer. And we know that the frequency is c over lambda, so this is hc over lambda, where lambda is the wavelength. So lambda equals hc over 0.37 EVs, and that's 3360 nanometers. At least that's what I got. Just a straightforward calculational problem. Part B, they want to know what the effective spring constant K is for the molecule. So remember, we're modeling this as a harmonic oscillator. So that means that there's something like a K. And the K, classically, we have E vibe equals 1/2 m omega squared equals 1/2 k delta x squared. Right? So that's the sort of idea. In terms of the vibrational energy levels, h bar omega, we're just substituting in for what the omega is in terms of a spring constant. So that's the same thing as h bar times k over mu, where mu is the reduced mass. You may remember this from freshman physics, except we didn't use reduced masses in freshman physics. So this would just be square root k over m. So in other words, we're making the correspondence, sorry, this is times x squared. We're making the correspondence omega squared equals k. So that's the basic idea. Now, here we're talking about the reduced mass, and it's for HCl. So mu sub HCl is the product of the two masses divided by the sum of masses. We found that out in section 3 of chapter 9. So this would be the mass of H times the mass of Cl divided by the mass of H plus the mass of Cl. And I just did this as a sort of a ratio thing. So this gives me K equals h bar omega quantity squared mu over h bar squared. And the reason I did that is I wanted to just use this without, sorry, it's just the way I did it. 0.37 EVs quantity squared, and then 35 over 36 for the mu. And then this is in ANUs. So to convert that, that's 1.67 times 10 to the minus 27 kilograms per AMUs. This is AMUs. And then I'm dividing by 6.56, excuse me, 58. Can't even read my handwriting. Times 10 to the minus 16 EV seconds squared. Yeah. So I get for this 510 newtons per meter. Everybody okay with my converting that to newtons per meter? This is actually kilograms per second squared, but that's the same thing as newtons per meter. Yeah, because a newton is a kilogram meter per second squared. A newton per meter is a kilogram per second squared, which is how this comes out. The EVs just cancel. Sorry, that's the way I did it. Okay, C. What resolution is required for a spectrometer to resolve the presence of H35Cl and H37Cl molecules in the vibrational spectrum? So those are apparently two different isotopes of chlorine, one with a mass of 35 and one with a mass of 37. As you can probably see from this, I was using 35. In AMUs, I mean, I was using this as 35 and this is 1, which is how I got 35/36. But what we want here is a difference in wavelengths. So the resolution we want is delta lambda over lambda. So it's a percentage difference, percentage change. So the only thing that's going to be different is the mu, right? So everything cancels out except the mu's since I'm taking a ratio. And I just get the square root of the mu for the 35 combination with the mu for the 37 combination minus the mu for the 35 combination. And we have to take the square root because the lambda just goes, lambda doesn't go like the k, right? The lambda goes like the square root of k. Everybody sort of okay? Everything else comes out in the bathwater. Okay, so so the mu for the 35 is what we just did here. That's 35, 36. So this is square root of 35, 36. And then we've got square root of 37, 38ths minus square root of 35, 36. So it's all pure numbers. So I get for that 1330. I did this upside down. Sorry, I meant to do this, but I did it backwards. Do you see that I did it backwards?
Yeah.
Sorry. Whatever that is, I don't know what it is. I must have been late at night when I was doing this arithmetic. Oh, sometimes I don't know where my brain is. Okay, very funny. All right, so that's 9:10. Let's move on to 9:12. Okay, so remember I said that the spherical harmonics formed a complete set. In 9:12, we're given a wave function, and we want to write it as a sum of spherical harmonics. And why do we want to do that? Because we're given the wave function and we're asked, what are the values that a measurement of L squared can yield? In other words, write it as a sum of spherical harmonics, and then we know exactly what the different values are. So the wave function that we're given is, go to the right page here. Psi of r equals x plus y plus z times some function of r. Right. Now, we don't know what the function of r is, but we don't care, because we're just asked for values that a measurement of L squared can yield, and this guy is a constant with respect to that. So all we have to do is write this x plus y plus z in terms of the spherical harmonics. And so I went to the table of spherical harmonics, which is on page, it's not all of them obviously, there's an infinite set, but the first few are on page 334. So from page 334, we get y1 comma 0 is square root 3 over 4 pi times cosine theta. y1 minus 1 is minus square root 3 over 8 pi times sine theta times e to the I phi. And y sub 1 minus, oh, this was plus 1, sorry. 1 and minus 1 is square root 3 over 8 pi sine theta be the minus I phi. Okay, so how are we going to do this? Well, the way we do this is we want to write x, y, and z in terms of spherical coordinates. Okay, so we can do that, or we can write these guys in terms of Cartesian coordinates. And for example, we know that r equals, or excuse me, z, z equals r cosine theta. So that means cosine theta is just z over r. So this is square root 3 over 4 pi z over r. We can also remember that this guy is x plus I y over r, because remember that x is r sine theta cosine phi, and y is r sine theta sine phi. So that means sine theta e to the I phi. If you add x and y, look, if you add x and y, x plus I y, you get r sine theta cosine phi plus I sine phi. And this is just e to the I phi. So that means that sine theta e to the I phi is just x plus I y over r. Do you see that? And similarly, this is 3 over 8 pi x minus iy over r. Okay, so that means that I can just add and subtract these guys. This will give me any z amount I want. The combinations of these guys will give me x and y. So that means that psi of r, let me get all my signs in the right place here. S-I-G-N, I mean. So psi of r is square root 2 pi over 3. That's to get rid of the whatevers. Y of 1 minus 1 minus y of 1, 1 plus I y of 1 minus 1 plus y of 1, 1. Right? So I'm not done yet, but I just want you to see how I've managed to put together these two guys so as to make x plus y. If I subtract these two, then the x parts will add and the y parts will add. Yeah? Excuse me, the x parts will go away and the y parts will add if I add them. If I subtract them, let's see, if I add them, wait. Have I done that right? Yeah, if I add them, the x parts go away and the y parts add. If I subtract them, the y parts go away and the x parts add. So this is x, and this is y. Right, but I still have to put in the cosine, the z part. So that's going to be, let's see, plus square root of 2, because of this, it's got a different consonant in front. Square root of 2 y 1 0. And then there's the r part, so I got to multiply everybody by r, and then of course everybody has the f of r. This is a fairly simple example, which you can more or less do by inspection, as I did. For more complicated ones, it might be a little harder, I don't know. But the y's, the spherical harmonics, do form a complete set. So any function you want at all, you can express in terms of the spherical harmonics. I mean, they won't always be this easy to do. Okay, so now that we've done that, let's finish the prob. This is not a very good example. Let's go to this one. Part A wanted to know what possible values can we get if we measure L squared. So measure L squared. That means I operate with L squared on this function psi. That's the if you look at all of these things, all of these spherical harmonics have the same value of little l, which is 1. So that means that no matter what, I'm going to get an L value of 1. So this is just going to give me h bar squared L plus 1 times the psi back again, where L equals 1. So this is 2 h bar squared psi. Have I done that right? I hope. Okay, that was easy. But then the second question is, what values can be obtained by measuring LZ? B, measure LZ. So if we operate with LZ on this function, what do we get? Well, if you ignore the number out in front and just look at the relative numbers inside, what do you get? Well, you've got, just in terms of relative numbers, in terms of the y 1 minus 1, you've got 1 plus I times y 1 minus 1, and you've got 1 minus I minus 1 plus I, sorry, times y of 1, 1. Can you see that in terms of the relative numbers? Right. But what are the probabilities? Well, the probabilities will be the amplitudes squared. Right? So what's 1 plus I absolute magnitude squared, and what's I minus 1 absolute magnitude squared? They're both square root of 2, or square root of 2 squared. So that means that the probability of getting minus 1 is the same as the probability of getting 1. Well, and also the same as the probability of getting 0. So if all the probabilities are the same, the probabilities must be 1/3 each, because those are the only possibilities of getting this. So could get h bar times 0, 1, or minus 1 with prob 1/3 each. So you could get any of the 3 possibilities for a total angular momentum of number of 1. Everybody okay? Yeah. All right, so that's number 12. And we did number 14 last week. So let's go to number 16. Boy, am I glad I did 14 already. Okay. 16 is a similar problem to what we were discussing in that section. It's about the raising and lowering operators. It says obtain y1, 0 by application of the lowering operator to y1, 1. Remember that what happens when you lowerify, let's see, this is, all right, where did I put it? Here it is. L minus is square root h bar, square root h bar times, well, L minus operating on L comma m is h bar times L times L plus 1 minus m times m minus 1. Well, this is plus minus, so this is plus minus. And then L comma m minus 1. Right. I just copied that from chapter 3. Right. So that's the lowering operator operating on a 1 of the L comma m eigenstates. And notice that it lowers your m, but doesn't do anything to your L. In other words, all it's doing is leaving your total angular momentum the same. It's just reducing the amount that is projected onto the z-axis. So once we've solved the differential equation for one of the YLMs, we can use a lowering operator or a raising operator to get the others. Okay? So he says, okay, let's find, well, we had y1, 1, which I wrote down here someplace. Here it is. Right, and we're just going to operate with L minus, this is number 16, L minus on y 1 comma 1. And that should give us h bar times the square root of 1 times 1 plus 1 minus 1 times 1 minus 1, right, because we're doing the lowering operator, so, and this was m plus or minus, so it's 1 minus 1, which of course is 0, times L comma 0, right, which is, this is y 1 comma 0. Everybody sort of okay? So this term goes away, because 1 minus 1 is 0. So you just get h bar times square root 2 times y 1, 0. Oh, sorry, I forgot to put brackets on him. Everybody okay? Yeah, all right. So let's do that. Remember that we know what L minus is. L minus is operating on 1 comma 1 is minus h bar over I e to the minus I phi minus I d by d theta minus cotangent theta d by d phi operating on, and I'm just copying it from over there, 3 over 8 pi sine theta e to the I phi. The only thing I've done here is I've just moved the minus sign out in front here so I didn't mess myself up. There's actually a minus sign here, but I put it out here. I like to have my minus signs in the clear, so to speak. Okay, so remember how we do this from that horrible problem 14 that I wasted so much time on last week. We have to operate everything going on in this direction. So this is the same as minus I d by d theta of minus cotangent theta d by d phi. We can take this guy outside. Sine theta e to the I phi. And this guy operating on that. So let's do the insides first. So I'm taking that guy over the other side. So that's minus h bar over I, square root 3 over 8 pi, minus I d by d theta, minus this guy operating on this. So the cotangent theta, nothing happens to in this term here. And nothing happens to the sine theta either, so that comes out here, right? But d by d phi, this does happen. So this is minus I, or plus I, excuse me, the minus sign's here, e to the I phi. Right, so that's the first iteration, right? Cotangent, sine, and an I. Okay. Now we have to take the derivative with respect to theta, okay, of this guy here. So this is, remember this is a minus sign, so let's see, wait. This is this, and this is plus, minus, wait, cosine? Minus cosine, minus I cosine, minus I cosine theta, e to the I phi. Yay! All right, now, the nice thing is all the i's cancel. So I'm going to cancel this I with this I with this I. Yay, all my i's cancel. All right, and the cotangent, of course, is the cosine over the sine. So those guys go away. And so I just get cosine theta and cosine theta, and those are both exactly the same. So this will be 2 cosine theta e to the I phi, unless I screwed up. So that's, and the minus sign cancels this one, sinus cancels this one. So I finally get plus h bar, square root 3 over 8 pi, 2 cosine theta e to the I phi. And I can get rid of this guy by taking out, let's see, do I want to take that out? Yeah, I do. Square root of 2, and then this is a 4 pi, and this is a 3. And the reason I want to take out a square root of 2 is because I got a square root of 2 over there. So this is the same thing as h bar times square root of 2 times square root 3 over 4 pi cosine theta. What happened to the e to the I phi? Did I screw up the e to the I phi? I did, but it's okay. You know why? I forgot to copy it down from here. So this guy cancels this guy, cancels this guy. So this goes away. Thank you. My arithmetic seems more than a little challenged today. Sorry about that. I should have looked at my paper. So in fact, we do get the right result. Although that took a while. Probably too long, longer than it should have. Oh, okay. Irritatingly, that was only part A. So we want to do part B as well. Right. Do I want those things? Well, I'm going to need y11. Yeah, but that's all I'm going to need. I wanted to keep these up while I was doing that. And I don't need this. All right, so part B. This might be the last problem I have time for, depending on how much I mess up this algebra. We want to do L squared. Okay, we want to apply L squared operator on y11 and show that it's an eigenfunction of L squared. So this is part B of number 16. This was part A. This is part B. So in part B, I'm operating with L squared on this guy. And what I hope is that I get back a a number times the same function back again. So what I'm going to do is copy the expression given for L squared in position space in spherical coordinates, which is equation 9, 129. So that looks like minus h bar squared 1 over sine theta d by d theta sine theta d by d theta plus 1 over sine squared theta d squared d phi squared. So modulo the constant out in front, this whole thing is just equal to this operating on sine theta e to the I phi. Okay? Okay, all right. Right, so this is minus h bar squared. All right. Let's again do it from the inside out. So first I'm going to operate this term on this. So this will be 1 over sine squared theta, and according to, these are just derivatives with respect to phi, so sine theta is just a constant, so that comes out in front, and we get d squared d phi squared of e to the I phi. And all that's going to happen is I'm going to bring down two factors of I, so I just get minus, and one of these signs cancels, minus e to the I phi over sine theta. Okay, and what do I get here? Okay, so now I'm going to operate with this on this. So I have 1 over sine theta d by d theta of sine theta d by d theta of sine theta e to the I phi. Okay, d by theta of this. How am I doing? I think I did it right. Ah! Now, this part on the inside here, the e to the I phi is just a constant. Okay, so I can take him totally outside, actually. Right? So d by d theta of sine theta, of course, is just cosine theta. So this is cosine theta. Now d by d theta of sine theta cosine theta, by the product rule, is, so we've got e to the I phi over sine theta, that's out in front. And then we've got d by d theta of sine theta, which is cosine theta times cosine theta, plus, or minus, d by d theta of cosine theta times sine theta, which is minus sine theta. So far, so good? I think so. All right, so the whole thing then is minus h bar squared, and I can take out this e to the I phi and the e to the I phi there. Everybody's multiplied by e to the I phi. Right, and we've got minus h bar squared, right. And we've got cosine squared theta minus sine squared theta minus 1. Yay! Which is minus h bar squared e to the I phi, oh, sorry, over sine theta. Over sine theta times minus 2 sine squared theta, which is 2 h bar squared sine theta e to the I phi. And remember, we wanted to show that when we operated with L squared on sine theta e to the I phi, we got back a number times the same thing back again. So we did get a number times the same thing back again. This is 2 h bar squared times the same thing back again. So this is the eigenvalue. And it's exactly the eigenvalue that we want, because L squared operating, remember this was y sub 1, 1. So if L squared operates on y 1, 1, you should get back h bar squared L times L plus 1 times y 1, 1. And this, of course, is just 2. So amazingly, my arithmetic, A, worked out, and B, I didn't screw up anything. I guess that's both the same thing, A and A. All right, well, we're a little bit over time, but not very much this time. I'll see you on Wednesday, and we'll finish up chapter 9. And please bring any questions that you have on any of the P-sets. It'd be really nice if everybody could get their P-sets done before next week. But if it doesn't happen, it doesn't happen.